I need to write down a very big formula, so I just prepare it on the blackboard. So this is so I already give outline of the proof of our proof. And as I mentioned, that the first step is Mochizuki formula. So we assume X to be projective surface. And we still assume the same assumption. B plus is greater than or equal to 3 and B1 equals 0. And I take H ample line bundle. And MHY. This is a modular space. Semi-stable. Torsion free sheaves, DZ. So in fact, I'm slightly cheating because if rank is 2 and if first chunk is even, then this is, you must consider the semi-stable shift, which is not necessarily stable shift. Then you cannot really develop the virtual fundamental cycle. So Mochizuki somehow modify, consider in that case, Mochizuki consider slightly different modular space and make, instead of directly defining integration over this, so he somehow replaced this space by some nicer space, and he defined the invariants by using such this modified modular space, which is stability and semi-stability are the same. But for simplicity, I just omit this technical part, and I treat this space as virtual obstruction theory, perfect obstruction theory. So then Mochizuki. So mu is is defined in the same way as before. So in the definition of Donaldson invariant. So you exponentiate and take integral over this modular space with respect to virtual fundamental cycle. And Mochizuki expressed it in terms of Seiberg-Witten invariants. So this is a sum, finite sum over Seiberg-Witten invariant. And Xi1 is, by some reason, so I need to use two notation Xi1 and Xi1 tilde. But they are just simply related by this, so it's basically the same. So anyway, so this turns out to be Donaldson invariant. It's equal to the sum over Seiberg-Witten invariant, linear combination of Seiberg-Witten invariant, and the coefficient is given by residue at A equal infinity, and this expression. And this expression is given by integration of some cohomology class of Hilbert scheme of points. So X Xn is Hilbert scheme. And as I mentioned, this is a resolution of singularity of symmetric power. And I still need to explain it a bit more. So I1 is a point in the first. So this is more precisely, you consider pairs of Hilbert scheme points. And so I1 is, so this is the ideal sheaf. I consider this the ideal sheaf and in the first Hilbert scheme. And I2 is a point in the second Hilbert scheme. And then I consider sheaf, which is just given by tensor. So this is a line bundle whose first chunk class is Xi1. And this is line bundle. So ideal sheaf twisted by line bundle. And A is a variable, but I consider it is an equivalent variable. So A is as I said, this is coming from the localization formula. So A is H2 of S1 point. And I consider exponential of A as a character of this group S1. So e to the 2A is just 2S2 square. But so anyway, this is a trivial line bundle, but with non-trivial S1 action. So this is an explanation of notation.
I missed the definition I1. What is it?
I1 is ideal sheaf. So Hilbert scheme points parameterize ideal sheaf. So this is a collection of points, but instead of so you have two way of viewing this. So either this collection of points or ideal sheaf. So if this is Z, so this is O of X divided by O. No. So Z O of Z is O of X divided by ideal. So this is ideal sheaf vanishing at those points.
So it is somehow parameterized by Hilbert scheme and the sheaf on X.
What is in the interval? What do you mean by mu as alpha Z?
Mu is so on this Hilbert scheme points you can define the same the mu class in the same way. So mu X is again modular space. You have.
I see. Okay.
So on X cross Xn, so you have universal ideal sheaf. Well, maybe just imagine that you consider so E1 plus E2. So this is a rank 2 sheaf. So E is equals. Then mu is so this is not stable in the usual sense. So you must be just imagine that. So instead of moduli, so you use E instead of universal sheaf or in the definition of Donaldson invariance. And this is exactly the same. And the additional piece is that H star is a section. Section B1. So this is a virtual bundle, and you consider its equivalent Euler class. And so this, I consider this is a formal power series in A and A inverse. So so this equivalent Euler class is well defined if I invert it. And the denominator is this alternating X2 groups between E1 and E2. So this is coming from normal bundle. Okay. So
the A in the exponent is reporting the C star action?
A is the equivalent variable for this C star action. Okay, I just explain the strategy of proof. So then I hope it will become the meaning of the formula becomes more clear. And this formula is I mean, of course, you must develop this virtual things and perfect abstraction theory, but somehow you can. Once such a things are prepared, then the remaining step is quite general. So you just consider so-called master space. So this is coming from when you study the change of stability condition. In geometric invariant theory. So suppose you have a space Q and group action, and you want to consider the GIT quotient of Q divided by G, and you suppose you have two line bundles, L plus L minus G line bundles, G equivalent. then you can, so the stability depends on the choice of this equivalent line bundle. So you can consider two DIT quotients to divide by. So then you want to compare the integral. So suppose you have a class alpha, the equivalent homology class in. Then, so this is a, I mean, I only consider the case when stability and semi-stability are inside. So you just restrict to stable locus, which is open subset in GQ. And then, because this is a nice quotient, you have it gives class in H star of M plus minus. So I want to compare M plus integration over M plus and M minus. So in order to compare, so Mochizuki considered this kind. Maybe so I think this goes back much more old than Mochizuki's study. And but anyway, so this is standard things to consider. Maybe master space itself first appears in Tabe's work, I guess. So you consider the projective bundle of L plus and L plus inverse and L minus inverse. And then you have a natural polarization here, and you take the quotient by G. Then on this space, you have a natural C-star action. So just by scaling one of the factors. And so you consider the fixed point. Then one is just this component is 0 or this component is 0. So you have this M plus and M minus. But sometimes you have some intermediate spaces, which is usually called exceptional fixed point. So this happens because of some existence of stabilizers. So I assume this is proper. So everything is proper. Then, so you consider this integral alpha times A. So alpha is a class here, and A is as in H2 of S1 or C star. So alpha times A, so I consider the integral of alpha A over M master space and restrict at A equals 0. And this is by, since A equals 0, this is 0. Then I compute this as a fixed point formula. Then this is just coefficient or residue of A naught in MC star of alpha A, and you divide by the normal bundle. So this is just the usual localization formula for equivalent homology. Then you have the contribution for M plus and M minus. So that is just difference of this integral and this integral. And but as I mentioned, there's some exceptional fixed points. So you have so this is final form is residue A equals 0, sigma p of fp, and this E of normal bundle. Times alpha. So this is the result. And here I assume that this M is smooth. Otherwise, I mean, I need to consider that so the normal bundle doesn't make sense. But once you, instead of smoothness of M, if you have a perfect obstruction theory, you can treat M as a smooth space. So everything you make everything in virtual, then this argument does work.
These spaces are non-compact.
No, this is, I mean, Q is a quarter scheme, so this is compact. So we are considering this modular space on projective surface. So these are compact. And so Mochizuki case, roughly, in Mochizuki's formula, you take M plus minus modular space of some stable, semi-stable pairs, E and S. So E is a rank 2 sheaf, and S is a section. And in this case, I mean, of course, you first choose ample line bundle H to define modular space of sheaves. But here, I mean, in fact, so the integration, I didn't mention, but this integration is independent of H. So if this B plus is greater than or 3, so this is well known for the case of Donaldson invariant, and it's Mochizuki also proves that for projective surface case. So anyway, that is not the polarization, ample line bundle which we want to change. But here it's a pairs, we are considering pairs of bundles and sections. So so this H is a polarization for E, but we still have a possibility to change the polarization for S part. So you have one more parameter of polarization. So he changed. He considered this. He changed to polarization for this part and use this machinery. And this is S. So this is section part. So on Tuesday, I slightly cheated. So this, I said S1 action is coming from S. But in fact, this S1 action is coming from this master space more precisely. And anyway, so this, Mochizuki also saw that M plus is a projective bundle over MH for suitable choice H. And M minus becomes empty. So this is, I mean, this already observed for the curve case by Tabeus a long time ago. So he used this observation to compute some integration over modular space of bundles on curves. So this part is Mochizuki used his idea. And this exceptional. This corresponds, as I said, E equals U1 plus E2. So, like in here. So this is rank 2, E1 plus E2 is rank 2 sheaf, which is direct sum of rank 1s. As I said, this exceptional fixed point is coming from the non-trivialness of the stabilizers. So if you have exceptional point, fixed point, then it must be decomposed like this. And both must be rank 1. So this is a line bundle twisted by ideal sheaf. So in this way, you get this formula, and this is a normal bundle. And this is a class which you integrate. So this is very roughly the strategy of the proof of this Mochizuki's formula. So any question or comment?
So if you look somehow more infinity type things, this ideal sheaf kind of regarded as a kind of point of bubbles.
Yes. This should be replaced by symmetric product, but you must be a little bit careful. This is. I'm not quite sure on symmetric powers you can make sense of this extended sheaf, because somehow this is usually in Uhlenbeck space that is a very singular point. And as I said, the smoothness or virtual smoothness are quite important to use this argument. And yeah, of course, one can develop the perfect obstruction theory in the C-infinity setting. Then somehow you must also make sense of this in general, more general for manifold for I mean, maybe you must replace symmetric powers, or I'm not sure, so I don't know. So nobody understands how you can.
In a different symmetric version, this parameter could be realized by some equation. You have a kind of a moment map equation.
Yeah. This is again moment map. So so this I only give a complex description, but you can also gauge theoretic partial differential equation. You can consider this part. Yeah, this part, I mean, is basically similar to Feehan length used, but still this essential difference, as far as I understand, is this. So Mochizuki developed this virtual obstructions, perfect obstruction theory, so that he can describe this coefficient explicitly in this kind of integral. So for topological application, maybe, so this means the Donaldson invariant is determined by Seiberg-Witten. So it's already close to Witten's formula. But if you carefully compare the two formulas, somehow you still see a big difference. The coefficient is much simpler. So this is very, I mean, N1 and N2 you cannot choose, so you must consider arbitrary number of points on. So this is a very complicated expression. On the other hand, this final expression is much simpler. So you must have some mechanism to from here, going from here to here. So this is non-trivial, still non-trivial. Okay, next step. So this is first step. Next step is universality. So so this part I don't want to go into detail, but it just says so to compute H tilde, this H tilde coefficient. It is enough to assume X to be toric surface, projective toric surface. So the answer, so this is due to Ames root Goettsche and Yoshioka. So they proved that this kind of integration of a Hilbert scheme of points can be expressed in the integration on the original surface. So this is very roughly, and integration. Maybe so you should compare it with this final expression, which I will going to explain later. So this is a generating function of this, and you and this is integration by Hilbert scheme. But at the end, it becomes just how to say the expression in, for example, xc1 and xc2 are cohomologic class in X, and this is an intersection number. So this is some function in the intersection numbers on X. So once you compute the expression for toric surface, and you read off this kind of expression, then these terms are the same for any surface. So this maybe better to return back after I explain this the final formula. So just at this moment, just believe me that in order to consider this expression for general surface, you just consider the case of toric surface. And as I mentioned on Tuesday, this is a little bit tricky point because toric surface is not the surface which we are really considering. But this coefficient makes sense for arbitrary surface. And now then we use torus action. And this we still use equivalent homology of this torus. And I introduce the variable epsilon and epsilon2 for those torus, equivalent homology of torus. And this appears in necklace of partition function.
Excuse me, let me
yes.
In your case, it's V2 plus is 1.
Mm-hmm. So both Donaldson invariant and Seiberg-Witten invariant are word crossings. Mm-hmm. So you said that in this equality, they both word cross, but this coefficient remains the same.
No. This is under the assumption B plus is equal greater than or equal to 3. So the cohort argument doesn't work in B plus equal 1 case.
So even if you include this word crossing, the word crossing does not occur in the same way. Donaldson part and Seiberg-Witten part.
Well, maybe I don't know. So maybe that is certainly much more complicated than this. But it could be, in principle, it could be possible, but I'm not quite sure you can derive some meaning from. So anyway, you can show the word crossing formula for B plus equal 1 using a similar technique. So then you get the similar kind of formula.
So this equality itself does not mean, but the left hand side a tilde doesn't make sense in the case of B2 plus, isn't it?
Yeah. So that's only say. So I don't claim that this formula makes sense for B plus. Just only this definition. And this, once you express this in terms of intersection numbers on original X, then the final answer is independent of the choice of X. So this is
function x0 in being defined yet?
No, not yet. No, so I already defined it. So this is integrated instanton counting partition function. So anyway, so I consider torus action, and xt2 is you have fixed point p1 to p chi. So chi is Euler number of X. And so you also have T2 on Hilbert scheme points. And the fixed point is again the same. Fixed point is again finite. And that is given like this. So maybe it is better to consider the zero-dimensional scheme. So Z is just Z1 plus G of chi. So you have several fixed points, P1, P2, and P chi. And so these G's are, so this is some fat point. So this is supported on those points. And each G, so if you choose a toric coordinate, around this. So this is x1, y1. So this is x2, y2. Then these GIs correspond to this T2 invariant subscheme supported at PI, and this is GI is this, and this corresponds to monomial ideals in xi and yi. Right? Then you draw a Young diagram. So this is xi and yi. So this is 1 and xi, yi, and so on. So GI, the structure C of GI is just these functions. So monomials surrounded by boxes. And in particular, so GI and GJ are not to talk to each other. So instead of this integration, so you imagine that you compute this by using localization theorem. And then, so those normal band, you don't need to worry some interaction between GI and GJ for different GI and GJ. So from this, so no interaction between PI and PJ, except those coming from the contribution of line bundles XC1, XC2. So these are global terms, so you must compute by in a different way. But contribution from GIs, or this I1, I2 are just coming from local contribution from this, and they don't talk to each other. So from this consideration, so it's enough to compute A for x is equal to C2. I hope this is clear. So now I introduce instanton counting. So any questions?
Got lost.
Line bundle. So this is not entirely in terms of Hilbert scheme. I mean, this line bundle is fixed, so you cannot see in this integral. But implicitly, E1, E2 are not this ideal shifts. I twist by line bundle. So even if I take N1, both N1 and N2 equal to 0, this integration is still non-trivial. So this is some. Yeah, I have a point, but still you have some non-trivial vector space and non-trivial action. So you must compute this contributions. So this is somehow I cannot. So because there's no point at all, I cannot make sense localize to PI or PJ. So I can localize this to. This is I consider this as an equivalent homology class, and I can restrict to fixed point. But somehow. This is somehow this computation different flavor from the computation for this coming from the Hilbert scheme points. So for Hilbert scheme points, part is much more difficult, and this part you can treat fixed point separately. That's clear. So that is the reason why and in the final formula I don't write something. So this explicit function, which is contribution from those line bundles. And then I have some expression which is coming from this Hilbert scheme point. Yeah. And this is just given by some computation from C2. So those F0 in is just given by some using instant modular space on C2. So that is roughly the strategy of the proof of this final form. Step 3 or step 4. So I will give a brief, this is of course introduced by Nekrasov and some years ago, and many of you already know that, but I will give the precise definition. So I consider C2, or I add line at infinity. So this is P2. And I consider Mn. So this is a Giesecke type modular space of instantons. Framed sheaves d phi on P2. So phi is rank 2. C is equal n. And phi is a framing. So this is Giesecke type modular space, and you have projection to Uhlenbeck type modular spaces. So this is partial. And there's an ADHM type description for both. That is the space of some linear matrices. And those two spaces are different by just change of stability condition. So anyway, so this is some concrete space, and this is also known to be, this is smooth. So this is one big, so complex manifold of the smooth dimension is equal to 4n. So this is one big good point. And you have, on this Mn, you have T2 and S1, so this is T3. This T2 is just T2 acting on C2. So this is the same as the toric. T2 appearing in the toric surface. And this S1 is the one which appeared in the first, this master space. And in this particular context, so this is a change of framing. So more precisely, I take e to the a to the 0, 0, e to the minus a. So this is in SU2. And I compose this trivialization with this matrix to get another framing. So this gives action on this framed modular space. And I consider corresponding the vector bundle which appears in the numerator. So I consider the corresponding one. So that is in physics literature called matter, fundamental matter. So this is H1 of E of minus L infinity. So in this case, H0 vanishes and only H1 survives. And by some technical reason, this I twist by square root of half canonical bundle, because this is kernel of Dirac operator. So this is fundamental matter. So this is a vector bundle V on Mn. So this is vector bundle. Rank n vector bundle whose fiber is this space. So this is a vector bundle. And so you have one more additional S1 action, one more additional. So in total, you have 4-dimensional Donaldson action. So this is a fiber-wise multiplication on V. Then I define instanton partition function. This is so I denote the corresponding variable by M. This is H2 S1 point. Epsilon is epsilon2 and A and M. And I also introduce variable lambda which count the instanton number n. So this is equal to sigma lambda 3n. And equals 0 to infinity of this Mn of e to v times e to m. So this I mean the trivial bundle, but with non-trivial this S1 action. So this tensor product just means I consider S1 action fiber-wise multiplication. So this is the definition of instant partition function. And you must be careful because Mn is, maybe I didn't say, Mn is non-compact. So Mn is a cousin of Hilbert scheme of points on C2. So you can, the point can be go to infinity. So this is so I did not explain why this is a partial contradiction. So you don't under symplectic product of S4, but you just under symplectic product, symmetric product of R4. Because of this reason, this is non-compact. Both spaces are non-compact. So this integration must be carefully defined. In fact, if this is compact, and this is, as I said, this is rank n, and this is dimension 4n, so degree and the dimension doesn't match. So if Mn is compact, this is 0. So of course, that doesn't make sense. So this is a this is a very important function. It contains those informations. So it is really crucial to consider this integration of a non-compact space. And this is defined by localization. So one quick way to define is the following. So on Mn, so this S1 is not so relevant. So I consider the torus, three-dimensional torus acting on this space. Then fixed points. What is fixed point? So first I consider this S1. So this frame. Framing action. Then it just means this E is equal to direct sum of rank 1 ideal shapes, and phi is compatible. So this I1, I2 are Hilbert scheme sum N1. So this is, in this case, this is C2. This is C2. And N1 plus N2 is equal to N. And if you compute the normal bundle, then you will see that this same kind of expression. So somehow, if you compute this for C2, then this is the integration which you really should consider. I hope this is clear. But in this particular case, it's even more simpler because, so there's only, so again we consider the Hilbert still have two-dimensional action on Hilbert scheme. And as I said, fixed points correspond to monomial ideas. And this is just correspond to partitions of Young diagrams. Of size n. Right? Then you can compute the tangent space. So you take a fixed point, so which is pairs of Young diagrams, and you compute the tangent space of Mn. So this. So this is Young diagrams, 2y, y1, y2, size is equal to n. So you still lambda 3n. So you have corresponding point E is equal to I1 plus I2 of Mn. And then you just EV tensor e to the m restricts to this. And I don't write down the formula, but this, everything, both denominator and numerator can be expressed in terms of Young diagrams. So this is some combinatory expression, but still it's really explicit. But in fact, let me see, what time is it? Still. But this is in some sense a little bit too much information because maybe I should also emphasize that because of this, this is not necessarily polynomials in epsilon, epsilon 2 equivalent variables. So this is rational functions in epsilon 1, epsilon 2, and a and m. And lambda is just a formal power series, right? So this is not the polynomial. So if, as I said, if this is compact, then this should be 0. But usually, if you consider, as in the case of master space, if you consider the equivalent integration over the compact space, you get polynomials in epsilon, epsilon, and s. But because we use just localization, so this is not polynomial. So this is a rational functions in s and. Maybe I should illustrate this meaning of integration. So this is a toy example. So we integrate function 1 over C2. So this is, according to this definition, you consider the fixed point, and so you divide, fixed point is just at the origin, and E of 0 at the C2 and 1. So this is the definition of this integration. And here we have C2 torus action coming from two-dimensional torus action. So this is just equal to epsilon 1 times epsilon 2. 1 over epsilon. Right? So similarly, this integration is some very complicated rational functions in those equivalent variables, and take this sum.
Could you have done this with rank 1? You had a question involving Hilbert schemes, but then you went to rank 2.
Rank 2. So yes, this is the two pairs of Young diagrams, and you have I1, I2. So in this case, you must treat by line to infinity. So this x1 can be computed, but somehow this is given some interaction between two Young diagrams. And if both are I1, both are the same, this expression is in fact appears in combinatorics of so-called MacDonald polynomial. So this is some famous function in symmetric function, and the people in combinatorics study quite a lot. But if those are different Young diagrams, then as far as I understand, those combinatoric expression never appeared in combinatorics. But nevertheless, this is some combinatorial expression. So in particular, you can write down the computer program to compute this for small number of n.
Is the degree of this rational function going to be determined by the relative?
Yeah, relative dimension of this, yeah. So, but somehow the integral, I didn't mention. So the final answer, this answer should not involve epsilon, epsilon2, because epsilon1, epsilon2 are additional torus action which we put when I consider the projective surface. Somehow you must forget epsilon and epsilon2. So it is important to understand the behavior of this function in epsilon1, epsilon2. And then one can show that this. So this epsilon1 over epsilon1, epsilon2, you cannot remove it. But the worst one is just to give this. So you take logarithm of this instanton partition function. So this is 1 over epsilon1, epsilon2 times f0. So by some reason, this is cost. There's instanton part and the perturbative part, and I always put in because this denotes instanton part. But so anyway, h in plus epsilon1, epsilon2 in plus epsilon. So this is symmetric in epsilon1, epsilon2. So that is all clear because there's no distinction between two factors of torus.
What is the epsilon 1 over epsilon 1, epsilon
To multiply in this expression, where do you close the parentheses?
This is starting.
Higher order.
So the worst pole is just 1 over epsilon1, epsilon2, which is coming from the integration of the base. And the other things are regular in epsilon, epsilon2. So this is the claim. And in fact, one can show that the coefficient of this epsilon plus epsilon2 is equal to 0. And the remaining function f0 in, a in, and b in are the functions which appears in this formula, final formula. So I repeat the formula again. So this A is a integral over Hilbert scheme, which we want to compute, and we consider the generating function. And as I said, this is independent of surface, so you can take x to be C2 and compute. And then you have some this explicit function, which is contribution from the line bundle, and the remaining part is just given by derivative of these functions. And so I don't want to explain all the how. I mean, this is a little complicated formula, so I don't want the detail or explain the detail. But I just want to explain the scheme.
I don't understand in this proposition what.
This is. I mean, it's a little bit difficult to. Yeah, in general, in theory, you could have more higher poles, But this claim is that this only has and because I mean you consider the symmetric powers, so this modular space basically contains something similar to symmetric powers. So yeah, it is a little bit. This is a little. If you don't know this kind of things, it's a little surprising. But by some cancellation of poles, the final answer. I mean, so I wrote this sum over y1 y2 and some expression, and this expression has much more worse poles than 1 over epsilon 1 epsilon 2. But after taking the summation, somehow poles cancels out, and you only remain this 1 over epsilon 1 epsilon 2. And the geometric reason behind is that this pole you cannot remove because this is coming from this. Maybe I just better to understand it to be after I explained how I derived this formula. So then I hope it becomes more clear. So this the function b xc1 xc of a. So this is a generating function is explicit function times. So the local contribution is over. So I have a fixed point p1, p2, and p chi. So I just multiply the local contribution. And the local contribution is this one, z in. But because, so each fixed point, you have this xi and yi, and you have weight of wxi and wiy. So this is the weight of torus action. So this is m1 of x epsilon 1 plus m2 of epsilon 2, or some m1, m2, and this is l1 epsilon 1 plus. So anyway, so you replace epsilon 1, epsilon 2 by this function. And A is just slightly, because of this global contribution, you have this. Yeah, anyway, so here I must write down. So you just compute this local expression. And you just localize it to fixed points of these PIs. And then, because of this Hilbert scheme point, if you consider generating function of Hilbert scheme, so this is something like exponential. Right? So the summation over fixed points become product over the fixed point. And the local contribution is this. So you replace epsilon 1, epsilon 2 by those local weights. And also A's and M's you must replace in this way. And then you take limit when epsilon 1, epsilon 2 go to 0, because the final answer you should forget these torus actions. Then,
so when you do these calculations, this CI is just contribute as a representation as PI.
This is I lift it to global class, equivalent class.
Yeah, but it's kind of global thing is just forgotten. Just it's the presentation.
Yes.
Yeah.
Yes. Then I just substitute this as exponential of this f0. So this is wxi, wyi over 1 f0 plus that. Then, for example, from this term, you get something like, so this exponential, you change the order and it becomes sum. So you get something like sum of I, wxi, wyi over 1, and square derivative df0 square d log lambda square and ipi exponential of I iota pi is the restriction. Alpha z plus. And this is independent of I, so you can put before. Then this is just exactly the formula, localization formula applied to toric surface. So this is just given by this expression, alpha squared, right? So this other intersection. So x is a zero-dimensional class, so x doesn't contribute. Only z square, alpha square becomes non-trivial, and this term appears in here. And all other terms are again the same. So you just expand this and take limit when epsilon 1 epsilon to go to 0. So you get this formula. And if this could happen, this logarithm of z have worse singularity, then somehow it is not compatible with localization formula for x. So in the localization formula for x, you always get Euler class of the tangent module. So for C2, this is epsilon 1 over epsilon 1 epsilon 2. And if you get something higher, then it is not compatible. And in fact, this is actually this proportion you can actually prove in quite a general setting. So if you have considered this kind of integral over Hilbert scheme points, and this integrand is something natural and having the multiplicative properties compatible with this understanding. So if you consider this joint union of x and 1 and x2, then the integral must be the sum, something like that. Some natural property you require, then always answer is having just only pole of 1 over epsilon 1 epsilon 2. That is quite a general result. Okay, so far I don't know. Yeah, but one thing. So tomorrow it becomes important that. So I introduce one more additional parameter m. So I have epsilon, epsilon 2, and a and m. M is coming from multiplication on fibers, and this m doesn't appear in Mochizuki's formula. And if you analyze this formula, so in fact he evaluates m at a. So this becomes important tomorrow. So I will come back. Now today I stop now here. Thank you for attention.
So what you wrote this explicit
contains some global behavior of Ci on X.
So this is some intersection elementary functions in Xi1, Xi1, Xi.
So the kind of, for example, Chang class is of Ci.
Yeah, Xi is Chang class. Already.
But I think it's the global of Xi that never appears in this kind of evidence.
Global of Xi appears. Global of Xi appears, but also how to say? that is a little tricky point because this final answer, so the final answer should depend only on Xi modulo 2, because you can twist line by line bundle. But the expression which we get is not so. So it's a little tricky point, but after taking residue, it becomes so. Yeah, expression I just omitted, but so you can look at in our paper. And it's just an elementary function.
I think it's known that if we just have a formula filled with an almost complex structure, one can define the Hilbert scheme.
Yes,
Probably one could define some of the Giesecke compactification. And then maybe in the
yeah.
ingredients make sense.
Yes.
Maybe one could just go through.
Yeah, and maybe I'd like to get to this. I want to comment one thing. So I expand log of z. And I said this is 0. But this is the first chunk class. Okay, first chunk class of C2. So if this term remains, then in the final formula, you have canonical bundles. I mean, you can still have canonical bundle, but the canonical bundle is always combined with C in this formula. So it means, I mean, if you really, so this you can consider as, how to say, a choice of spin C structure. And if you get something just involves only kx, then it should not be compatible with final expression because this should not, this is a smooth invariant and how to say. So this coefficient, in this coefficient, it should not be depending on the complex structure or even almost complex structure. And I cannot directly show this statement. We can show this statement vanishing, but it's not a non-trivial statement, and this is not automatic. And so it seems in this approach I really need to choose complex structure.
So are there any kind of intuitive reasons why storage case is enough to compute?
Well, but so if you believe that we should get this kind of formula, then so this is quite universal, just only in terms of intersection. I mean, but of course we want to prove this formula, so you cannot use this final answer to prove something. But well, still, I mean, this is still non-trivial result. I mean, you must analyze the structure of Hilbert scheme, and in particular, the proof by Goettsche doesn't really give the explicit formula. This is somehow algorithmic statement, algorithmic proof, and how to say. So you don't get any explicit number for this integration of Hilbert scheme points. So just some abstract existence.
So I think so far you used just the class of partition function, yes. But you didn't use the class of conjecture yet. So
no. So this is quite general. So this is quite a general story. You can consider much more general integration over modular space, but you always get a similar kind of expression. So Mochizuki's result is more general, so you can replace this integral by more general one. And here you get corresponding cohomology class on the Hilbert scheme. Then you just replace this definition of the necklace of function. So this is quite general. But in order to analyze those, in the final step, we really, I mean, if you compare this formula and the final formula, still it doesn't match.
So there this Seiberg-Witten curve appears.
Seiberg-Witten curve appears. So in order to compute those coefficients. So up to now, this is just a calculation. I mean, it's not so much involved, I guess. Just usual application of the localization formula, and then everything is reduced to C2. That is quite a general strategy. But final computation of this necklace of partition function is quite non-trivial. So that is the most difficult part.
Can you explain it tomorrow?
Tomorrow.
Okay. So tomorrow the talk is
I don't know what time.
From 11.
11.
Yeah, 11 o'clock. The same thing. Any more questions? So thank you very much again.